Okay, in this video we're going to review the Kepler's famous 3 laws of planetary motion. Now before we get to Kepler, I want to just mention and give a shout out to Tycho Brahe, who was Kepler's mentor. Brahe was one of the great astronomers of the ancient world, and he was someone who worked with a team for many, many years to record the positions of the stars and the planets in the night sky. And what he had to do it with was a very, very crude instrument by today's standards. Now here's a representation of Brahe's telescope, which the word telescope is in quotes up at the top because it's not a telescope in the traditional sense. There are no lenses, it's not a tube. There are no mirrors or anything like that. It's essentially just a big protractor, and what he did was he lined up the position of the stars with the protractor and he measured the elevation in the sky, and this thing would actually pivot along different angles, and he could measure the position in the sky by 2 angles. Because his telescope had no lenses, he's sometimes called the last of the naked eye astronomers. And so really the work done by Tycho Brahe was the sort of division between what we call ancient astronomy and modern astronomy. We consider modern astronomy to begin with the invention of the telescope. Now, one of Brahe's colleagues and students was a guy named Johannes Kepler. And when Brahe died, Kepler received all the data that Brahe and his team had been taking over these many, many years. And Kepler was a mathematical genius. He was able to pore through all these data with just the positions of the planets every night, recorded as different angles. And he was able to analyze that data and suss out 3 very, very powerful mathematical relationships that give us an incredible amount of information about how planets move around the sun. Now, Kepler's first law of planetary motion says that the planets move about the sun in elliptical orbits with the sun at one focus. Now, an ellipse is not just an oval. It's a curve that's oval-shaped, but that follows a specific mathematical relationship. And so that was pretty startling that the planets could be moving along a path that you could describe with a mathematical equation. Now, ellipses are characterized by having 2 focus points, and what Kepler's law says is that the sun is at one of the 2 focus points, and the other focus point is just someplace in outer space. But they're along this line here. This line is the longest line that you can cross the ellipse with, and that's called the major axis. And from the center to the focus is the same for each focus. Now we can see a more mathematical representation of an ellipse. If we have this distance being the major axis, halfway from the center to the edge along the longest line, that's called the semi-major axis. Like a semicircle is half of a circle, the semi-major axis is half of the major axis. And the 2 foci are labeled here as F and F prime. And there's another value here which is called the eccentricity. And the eccentricity basically depends on the distance from the focus to the center of the ellipse. Now I said that an ellipse is defined by these 2 foci. How is it defined by 2 foci? Well, simply, you pick a point on the ellipse, say a point right here, and you draw the distance from each focal point or from each foci to that point on the ellipse. And if I add this distance r prime plus r, that number will be the same for any point on the ellipse. So if I come down here and I make this point my point, say right there, and I draw this distance, and I draw that distance plus that distance will be the same as the red distances added together. So that distance, those 2 distances added together have to be the same as those 2 distances added together. And that will be the same for any of the points on the ellipse. Now in this slide, I'm showing you a picture that has different eccentricities. Remember, the eccentricity involves that distance from the center to the focal point. And so this here would be a different eccentricity than that there, for example. And here we can see each of these eccentricity values for these different shapes. Now, one thing that's worth noting is that the eccentricity is 0. That means there's no distance between the focal point and the center. Both of those focal points will then converge to the center, and what you have is that the ellipse turns into a circle. Now, as the eccentricity gets bigger and bigger, the ellipse gets squashed out and it becomes more and more elongated. And here we see the eccentricity of 0.96, that's almost 1, and the closer the eccentricity gets to 1, the flatter the ellipse becomes. It becomes more like a line rather than a circle. Moving on now to Kepler's second law, we know that the second law states that an imaginary line drawn from the sun to a planet will sweep out equal areas in equal times. So if I have the planet here is orbiting along this elliptical path. When the planet's here, if I draw a line from the sun to the planet, and I pick a time interval, the time interval could be any time interval I want, a week, a month, 6 months, whatever. Let's say in this example it might be, say, a month. So in a month, on this side of the orbit, the planet moves along this ellipse from there to there, so from there to there, and this line that connects the planet to the sun sweeps out an area. And that area will be the same for every time interval that has the same time interval. So if from here to here takes a month, on the other side of the orbit, it would only go from here to here in a month. It's slower. It's moving much more slower. But the relationship is that that area swept out will be equal. So here we see these two blue areas, which are the areas swept out by the planet in these two equal time intervals, and those areas are equal. Now, practically what that means is that when the planet is moving closer to the sun, it's going faster, and when the planet is moving farther away from the sun, it's moving more slowly. One of the ways that you can think about this is to imagine the gravity. So when the planet is moving along this path, the gravity of the sun is pulling it and slowing it down, so it's going slower and slower and slower. But when it turns around and it starts moving back towards the sun, the gravity is speeding it up so that it goes faster and faster. So on this side of the sun, it whips around very fast, and on that side of the sun, it moves more slowly. And again, it's not just the planet is speeding up and slowing down. This geometrical relationship involving the areas tells us that this is happening in a way that can be predicted by mathematics. And so that was a very powerful relationship that helped us understand how the planets move around the sun. Now, Kepler's third law involves the size of the orbit to how long it takes for the orbit to go around its complete path. Now, this is sometimes called the harmonic law, but here I've shown it for various circular orbits. So we might have a body, which could be a planet, say like the planet Earth. We could have the Earth's moon. There could be a man-made satellite here. There could be another moon, very, very small moon, say some captured asteroid or something. And if we go out to the radius of these circular orbits, the mathematical relationship says that the time it takes to go around the planet squared divided by the radius cubed is some constant value. It would be the same for all of these different orbits. And so this applies to circular orbits, but it can also apply to the elliptical orbits that we saw with the planets according to Kepler's first law. So if we consider a planet, what Kepler's third law says is that the period of the planet measured in years, that's the period of the planet measured in years, squared, is equal to the semi-major axis. Remember, that's half the major axis. So the major axis is the longest line that you can cross the ellipse with. The semi-major axis goes from the center out along that line, and it's half the distance. And so you take the semi-major axis and you cube it. That is, you multiply it by itself 3 times, and that gives you the relationship between the size of the orbit and how long it takes to go around. once again, we see that these motion effects are described by mathematical relationships, which is, of course, math is the tool that is used to describe things in physics and astronomy, and it can be a very powerful tool for understanding the way that our universe works. Okay, so you should be ready to go on to the next part of the module and proceed with the rest of this lab.